And our final talk will be given by Matthias Kannwischer on behalf of the authors of the paper, who unfortunately could not make it. It's a systematization of knowledge on the physical security of UOV-based signature schemes. Matthias?
All right, thank you very much for the introduction. So this is work by Thomas Albach, Fabio Campos, and Julian Kramer. Unfortunately, all three couldn't make it to the conference, so they asked me to give this talk for them. So I'll try my best to represent their work. They prepared the slides, so if I'm saying something that's inconsistent with what's on the slide, probably the slide is right and I'm wrong, but we'll see. So let's start with a motivation for this work. So there's this old crypto system called UOV that was proposed in the 90s that has very small signatures, but rather massive public keys. And that can be quite useful for certain applications. And after this was proposed, a couple of other schemes came out that improved upon this. So there was one scheme called Rainbow, another scheme called LUOV. And these were actually candidates in the last NIST competition. And they have smaller public keys than UOV, so they look more promising. Unfortunately, now they don't look so promising anymore because they got completely broken as a part of the NIST process. But UOV itself did not get broken, and is now a candidate in the current NIST competition for additional signatures. Furthermore, there's more schemes that are based on the general UOV construction. So for example, there's one scheme called Mayo that is also a candidate in the second round of the current NIST competition. And there are a couple of more. So there's QRUOV and Snova, also candidates in the second round. And in the first round, there have been 3 more called Vox, PRUOV, and TUOV. So there's quite a few schemes based on UOV. And some of them are quite promising. So of course, over the years, many people have looked into side channel attacks on some of their schemes. Some only studied UOV, some only studied others, some studied multiple schemes at once. So there have been fault attacks on UOV. There have been single trace side channel attacks on UOV. There have been row hammer attacks on LUOV. There have been more fault attacks on UOV. And a couple of more papers on Rainbow and UOV, and a recent paper on Mayo. So the logical question here is, how does this all fit together? So do all of these attacks apply equally to all of them, or is there some attacks that only work for some? Or so that's the general question that the authors have looked into in this work. So there's a variety of attacks on several UOV-based schemes. There are some attacks that target old or broken schemes, so those are probably no longer relevant. And furthermore, there's no implementations of any of these that the authors or I am aware of that protect against physical attacks. So the goal of this work was to first analyze how these different attacks transfer between the schemes, to get a more complete picture of the vulnerabilities, and in particular also look into the 4 candidates that we now have in the current NIST competition, on how all these attacks that are there in the literature apply to those. Then the authors also wanted to investigate, if we take the countermeasures that have been proposed in these works and apply them to the schemes, how will the overhead actually look like? So let's start with some background on multivariate cryptography. And this is the same for all the schemes that are candidates now. So the general object that we're working on here are multivariate quadratic maps. These are maps that map a vector of elements in FQ to another vector of elements in FQ. And usually here n is referred to the number of elements in a signature, and m is the number of elements in a message. So these maps map signatures to messages. And P is constructed in a way that it consists of m homogeneous quadratic polynomials. And then signing works in the following way. If you want to sign a message D, you apply a hash function to this message to get a target vector T. So this is going to be kind of the message that we are signing that consists of M elements. And signing then finds a pre-image of T. So you try to find an S, that's a vector of N elements, and if you throw that into P, that should give you T. And in general, this is really difficult. So we need to include a trapdoor to make this actually feasible and fast. And that's going to be on the next slide. Verification then is very simple. You take your signature S, apply the public map P to this, and check that this actually gives you T, the hash of the message. So how do we actually construct this trapdoor? It's kind of the core of all multivariate schemes. How do we construct this map so that we can actually efficiently invert it if we have the secret key? So the way this works in UOV is we define, we use a subspace of, that's called the secret linear oil space, and we construct P in a way so that for every vector in this oil space, the map P vanishes. So if you take any vector from this oil space O, throw it into P, what you get out is a vector of all zeros. So how does this help us with solving this this inversion? So finding a pre-image. One way to look at this is, there's multiple ways to define this, but one way is the following. We can look at the bilinear and symmetric differential form. So if we look at that, that's defined as P applied to X plus Y minus P applied to X plus P applied to Y. And can look into how we can then use this to sign. So if we want to find a pre-image, we can find a pre-image that's exactly constructed as the addition of two vectors. One we usually call the vinegar vector, the other we call the oil vector. One of them we can pick randomly, the vinegar vector we pick randomly, and then we can plug it into this differential form. And what we see then is that for the constant, the fixed one, we can plug it in and we get a constant out of that. For the oil vector, this will vanish, so it will be 0. And for the differential form, this is going to be linear, So what we end up with is a system of linear equations, and this we can efficiently solve. So this, we can now look into more in how we write this down as an algorithm. So for signing, for finding this pre-image, all of these schemes usually use the following 5 steps. So the first was the computation of the target vector. It's just the application of a hash to the message and usually a salt. Then we randomly generate these vinegar vectors, these vinegar variables. We can then plug that into the previous equation, which will give us a linear system of equations, and that we can then just solve using Gaussian elimination. The last step is then we compute the signature as the addition of this vinegar vector and this oil vector. And then it will hold that if we apply the public map to this, it will give us the target vector T. So that's the 5 steps that UOV is using in signing. If you look at the specification that is now on the NIST website, you will find an algorithm called sign in there, and you can then define the 5 steps in there. First, you derive the target vector. Second, you sample the random vinegar vector. Then you set up a linear system of equations. You solve that system, and then you add together the oil and the vinegar part. Yeah, and this is essentially present in all UOV-based schemes. So you can look at Mayo. There in the spec, you will find the same 5 steps. It looks a little bit more complex because there's more structure, but it's the same 5 basic steps. Same for SNOVA and QRUOV, the same 5 steps. So since they all follow kind of the same steps, it makes sense to think that attacks that attack these schemes will likewise apply to the other schemes. Some examples for this, one common attack is to reveal one of the vinegar vectors, or to make your implementation reuse a vinegar vector to sign two different messages. And so this equally applies to all of these schemes. All of these have many matrix vector multiplications, so conducting power analysis of these also applies to all of them, and so on. There's a couple of more examples of this. For example, this last step of adding the vinegar and the oil vector, if you can skip this, this addition, you end up with either the oil or the vinegar vector, and that is gonna break the scheme. However, of course, this is theoretical. In practice, there is a lot of things that this depends on, and how you then implement these different steps may prevent certain attacks from actually being effective. Could either be a countermeasure that someone implemented, or may just be coincidence that they implemented it differently and the attack doesn't apply. Okay, so let's look into these attacks a little bit in more detail. First, we need to understand what are the things that an attacker actually wants to recover in UOV. And of course, what an attacker needs to be able to sign is knowing the secret oil space O. And if you know this oil space, then you can forge signatures. So that's the valuable part that we want to recover. And it's relatively easy to see that you can efficiently recover this oil space by knowing just one oil vector in UOV and Mayo and a few oil vectors in Cure UOV and SNOVA. And the vinegar vectors here are almost equally valuable, because if you have a signature and a vinegar vector, then you can just subtract it and you get an oil vector. So these are kind of the things that attackers are after. If you recover one or maybe a few of those, then you break the scheme. As an implementer, of course, we want to protect those while maintaining efficiency. So let's look into how this looks like for fault attacks. So I've already mentioned this. So one common way to attack these schemes is by forcing the expansion, so the step where you derive the vinegar vector. This is usually by using a hash function or a XOF. So if you can force this to reuse the same vinegar vector for signing two different messages, you immediately break the scheme. But even if you can just leak this vinegar vector, then you can compute the oil vector. What is also commonly done is by inducing persistent faults into the secret keys, and this also is then very easy to attack the schemes. Another attack that is commonly applied is just skipping this last step of adding the vinegar and oil vector. So if you can skip that, you reveal either the vinegar and oil, and then from a signature you can compute the other. For side channel attacks, basically all of the field multiplications involving the oil and vinegar vectors are obviously vulnerable. So many attack papers have been published on how to attack those. And that means that most of signing in UOV is vulnerable, because that's the core operation that's happening in there. Okay, so now the authors looked into how can you transfer these attacks that have been published to the 4 schemes that are current candidates in this competition. So they looked into the fixing of the vinegar vector, row hammer attacks on the oil space, bit flips on the stored secret matrices, the prevention of this addition of the oil and vinegar vectors in the end, and disturbing the linear system setup. And what you can see here is check marks if the attack works on the current implementations that are part of the NIST competition, X's if the attack doesn't work, and stars if the attack works in theory, but in practice it's much harder than what was in the original papers. And maybe it's one more thing I should explain. So for UOV, you see 3 symbols. That's because UOV has 3 different variants: UOV Classic, UOV PKC, and UOV PKC SKC. So some of the attacks only work for the first 2, are a little harder than for the original one. For Mayo, there's 2 symbols here, where the first one is the deterministic signing and the second one is the randomized signing. Yeah, this could in theory be done for the other schemes, but Mayo is the only one where actually the spec has a randomized and a deterministic one. So overall picture is fault attacks, some of them carry over, some of them don't. But general picture is that if you have a deterministic scheme, it's very bad. If you have a randomized scheme, some attacks just won't work that easily. Okay, and of course this depends on implementation choices. So some attacks are simply stopped by this operation is implemented differently. Another observation here is that actually compressed keys that can be used in UOV, that are always used in Mayo, and also used in the other schemes, they actually are harder to attack because it makes it harder to have persistent faults in the keys, because these compressed keys need to be expanded every time you sign. And another operation, I think this is the obvious one, that randomized signing is needed to protect against fault attacks. So if you care about fault attacks, you should be using the randomized versions. Countermeasures for those usually are not very expensive, but they might be quite specific to your fault attacks. In terms of side channel attacks, we can see that most of the attacks that are in the literature equally apply to all of them. One of the attacks doesn't really work for randomized schemes, just because you can't, for certain multiplications, you can't run it multiple times with the same inputs because it's randomized, so it's going to be different every time. Yeah, so everything is easily transferred across these schemes. It's quite hard to protect because you have to protect all of the field multiplications. And masking will be quite expensive. In terms of countermeasures, yeah, this I've already mentioned. Some countermeasures are actually implementation choices that we also do for other reasons. For example, the key compression is something that we do for compressing keys, but it also helps against fault attacks. For many of these attacks, there's cheap mitigations. So that's not that expensive to implement here. This I've already mentioned. In the deterministic setting, a lot more parts are vulnerable, so you should really not be using the deterministic schemes if you care about fault attacks. Side channel attacks, you need to protect all the operations, including that operate on oil and vinegar vectors. And there is no mass implementations of those available yet at all. So the work by the authors here is the first that implements these schemes in mass. And they've done this for Mayo and UOV, by the way, the implementations of the countermeasures. They've then studied how the overhead of this masking, so this is first order masking, they studied this for Mayo and UOV. Maybe I skip to the conclusions. So for UOV, it's quite expensive since all of the operations there are basically sensitive, so you have to mask everything. For Mayo, it's a little better. That's mostly because some operations, it's not immediately obvious if they're sensitive or not. So the authors choose to not protect some of these operations here. That makes it a little more efficient. They've then conducted a TVLA test to check that their masked implementations are actually not leaking anymore. Of course, there may be more powerful attacks where first order masking is simply not enough. So that, of course, we still need to study more. Okay, with that, a few takeaways. So there's vulnerabilities that carry across carry to all of the UOV-based schemes. This is a systemization of this knowledge, so it brings together all the papers that have been done in this sphere before and applies them to the current candidates. randomized signing and compressed keys actually help us to protect against fault injection attacks. And in terms of other countermeasures, the fault injection attacks can usually be protected against quite cheaply. For the other side channel attacks, it's more difficult and more expensive. With that, I'd like to thank you for your attention. If you have deeper questions on this paper, you probably want to reach out to the authors. I can try to answer some simple questions if there are any. Thank you.
Thank you very much, Matthias. Yeah, Peter.
Try with a simple question. Do you have any educated guesses or inside information if the submission teams are working on incorporating the countermeasures, say, beyond first-order masking?
Yeah, so of course the submission teams have been informed of this work, and so yeah, I think in the long term we want to the submission teams want to do that, but since these are really the first implementations, there is still a lot of work, and I expect more papers in countermeasures and attacks.
Any other questions? Maybe then also a very generic one from my side. Is there any difference in how difficult it is to implement countermeasures for these schemes, or is it all the same and there's little difference?
So for the operations that are obviously need to be protected, it's quite similar. It is just that UOV is the very simple version of this. So for the other schemes, sometimes it's not quite clear which parts have to be protected, and so there is some difficulty in figuring that out. Besides that, I feel for the countermeasures in here, my impression is that this carries over. Maybe this would be more a question for the authors.
Perfect. Thank you. Anyone else? Then let's thank the speaker again.